I've mentioned definition of simple radical form in several previous lessons, and now it's time to give a textbook definition of simple radical form. A radical is said to be in simple radical form if 1. There are no radicals in the denominator, and 2. The radicand or radicands in the numerator are as small as possible. Well, in the previous lessons, we've addressed rule number 2, but there's been no mention of radicals in the denominator until this lesson. And in order to do that, we need to take a look at the square root of a quotient property, which has some similarities with the square root of a product property mentioned in the previous lesson. The square root of a quotient of two positive numbers equals the quotient of the square roots of the numbers. That is, for positive numbers x and y, the square root of x divided by y is equal to the square root of x divided by the square root of y. Let's take a look at a sample problem. We have root 39 divided by root 3. Well, we can apply the square root of a quotient property to change that to the square root of 39 divided by 3, which of course is 13. So it's simpler to write root 13 than our original expression, root 39 over root 3. Here's root 7 divided by root 5. Well, 5 does not go into 7, and since 7 and 5 are prime, the radicands are as small as possible. So now we're going to look at the rule where we try to get the radicands out of the denominator. The way we do that is we multiply the entire fraction by root 5 over root 5, because of course that's equal to 1, so we're applying the identity property by multiplying by 1. And then when we multiply, as we have learned for fractions, the numerator times the numerator makes root 35, and the two denominators multiply to make root 25. But of course, the square root of 25 is 5. And the numerator, 35, while not a prime, there's no perfect squares that go into 35, so that's as simple as it gets. And while it doesn't look that much simpler than the original expression, it fits the rules because mathematicians don't like radicands in the denominator. Here's another one. The square root of 50 divided by 63. Well, that fraction's already in lowest terms, so we're going to split it up and rationalize the denominator. But first, we'll get the radicands as small as possible. Well, of course, 50 is 25 times 2, and the square root of 25 is 5. And 63 is 9 times 7, and the square root of 9 is 3. Notice we've shown a little less work because we've been working on this for several lessons now. So now we have 5 root 2 over 3 root 7. And in order to rationalize the denominator, we'll recopy it on the next line, and at the same time we'll multiply the whole thing by root 7 over root 7. And of course our numerator now is 5 root 14, and our denominator is 3 root 49. But since the square root of 49 is 7, we go 3 times 7 to get 21, and now it's as simple as it gets. Here's 3 root 20 over 42 root 15. Well, the 3 over 42 is not in lowest terms to begin with because 42 is divisible by 3, so we'll simplify that right off the bat. And now, without showing all of our work, we'll apply the square root of a quotient property because root 20 over root 15 can be put in lower terms because 20 and 15 are both divisible by 5. So we now have root 4 over 14 root 3. Well, of course, the square root of 4 is 2, so we'll take care of that right now. And our only thing left is to rationalize the denominator by multiplying by root 3 over root 3. And then we get 2 root 3 over 14 root 9. Well, the square root of 9 is 3, and 14 times 3 is 42. We have 2 root 3 over 42. There's one more step because 2 goes into 42. We can put the fraction in even lower terms. We get root 3 over 21, and we finally put it in the simplest form possible. Here's a multiplication problem. None of the numbers under the radical symbols can be simplified any more than they already are. So we'll multiply through and get root 40 over root 45. But of course, 40 and 45 are both divisible by 5, so we apply our property once again, this time showing our work by putting it under the radical, and we get the square root of 8/9. Then we separate it out because the square root of 9 is 3, and of course the square root of 8 is 2 root 2 because 2 times 4 is 8, and the square root of 4 is 2. So 2 root 2 over 3 is simplest form for our original product that we started with. Now we have a division problem. Square root of 2 divided by the square root of 15 divided by the square root of 10/6. Well, right away we see that 10/6 can be put in lowest terms, so we change that to 5/3. And then we break it up, so we have root 2 over root 15 divided by root 5 over root 3. We apply the definition of division, which means to multiply by the reciprocal. Then we do the multiplication. We get root 6 over root 75. We apply our property because 6/75 can be put in lowest terms because both those numbers are divisible by 3. That gives us root 2 over root 25, and the square root of 25 is 5. So our final simplified form for the original division problem we were working on is root 2 over 5. Here's an addition problem. So we'll do some simplification, and we'll also be looking for some common denominators. But we'll start by simplifying the square root of 125 because that's 25 times 5, and the square root of 25 is 5, so we get 5 root 5. Then we see that we have a 30 over 5 in the second fraction. Well, they're both divisible by 5. So now we have 6 over root 5 as our second fraction. Well, the good news here is we now have a common denominator of root 5. So we add the numerators and we get 11 over root 5. And then to rationalize the denominator, we multiply by root 5 over itself. We get 11 root 5 over 5. We've shown a little less work. We know that root 5 times root 5 is root 25, and the square root of 25 is 5. Or another way to say it is root 5 times root 5 is 5. Or the square root of a number times the square root of the same number is equal to the number. And in this particular problem, we've gotten it to simplest form, 11 root 5 over 5. Here's a tricky problem, but we notice that we have two fractions that are being multiplied by 5, so we factor out the 5, and the first thing we're going to do is simplify the expression which is in those parentheses. So we're going to go to a clean slate and just write what was in the parentheses. Then we're going to apply our property. So we have root 5 over root 3 plus root 3 over root 5. We'll rationalize both denominators. We multiply one fraction by root 3 over root 3 and the other fraction by root 5 over root 5. Now both fractions have the same numerator, but one fraction has a denominator of 3 and the other has the denominator of 5. So our common denominator must be 15. We multiply the first fraction by 5 over 5 and the second fraction by 3 over 3. And there's our common denominator of 15. We simplify it even more. We get 8 root 15 over 15. And that's as simple as that expression gets. But remember, this expression was in parentheses as part of an even larger problem. So we're going to go back and substitute that into the parentheses as shown. Now we multiply it by 5. Easier to write it as 5 over 1. And then we can cancel out. And 5 divided by itself is 1. 15 divided by 5 is 3. So our final simplified answer is 8 root 15 over 3. Once again, the definition of simple radical form. A radical is said to be in simple radical form if 1, there are no radicals in the denominator, and 2, the radicand or radicands in the numerator are as small as possible. And then we have the square root of a quotient property. The square root of a quotient of two positive numbers equals the quotient of the square roots of the numbers. That is, for positive numbers x and y, the square root of x divided by y is equal to the square root of x divided by the square root of y.